Okay guys, let's continue our discussion on design philosophies, and the first methodology we are to consider is the allowable stress design. So the allowable stress design, or ASDs, defines a method of proportioning structural components such that the maximum stress calculated, assuming linearly elastic material behavior in theory, does not exceed the code specified allowable stresses when subjected to all appropriate load combination. Or simply your R, which is again the resistance that we are referring to on our last video, is equivalent to omega, factor of safety multiplied by the required strength Ra, where R is the nominal strength or the design strength, omega is the factor of safety, and Ra is the required strength. So basically ASD works on the premise of specifying the allowable stresses. That's why it's called an allowable stress design, because again, from the word itself, specifically the allowable stress is just specified. So who specifies the allowable stress? The code will take care of it. The expertise, the judgment of the committees who are working on the code will actually specify without any shall I say probabilistic or statistical justification on it for as long as the specified allowable stress are not exceeded if safety is dictated by the criteria given by this equation. Okay, remember that R is always greater or equal to Q, no? So here, Q refers to your Ra here. There's only a change in a variable considered in this particular aspect. But they mean the same thing. So for R and Q to be related in a way the factor of safety is measured, then a variable omega is inserted here to create an equivalence or a non-equivalence in this regard. So if you look into the allowable stress design procedure, the process is simpler as compared to the other procedure we will be discussing. Take note that ASD uses stresses rather than forces, but if you want to use forces, it's okay, it's fine. No? Only for standard code regulation, they normally give you allowable stresses instead of allowable loads. So values for omega changes from code to code based on experience, judgment, and expertise, and not based on probabilities. So for beams and tension, for example, the American code uses 1.67, columns 1.67 to 1.92, and connections 2.5 to 3.0. So these ranges of factor of safety are again based on experience and expert opinion. No probability in its detailed form were used to validate such factors of safety. So for the values of the factor of safety based on probabilities, we will be discussing this later on, and I'd like to show you that the measurement of such factors of safety for the LRFD procedure, which is based on probability, is quite confusing. That's why for ASD comparison, the LRFD is a little bit more involved in terms of the inclusion of the factors of safety involved. Okay, Okay, so note that the coefficient of 0.75 here are still not probability-based load factors. They are there to account for the likelihood that all loads applied will be a maximum during their lifetime. The other factors account for the load's 70% earthquake being reduced to the service load level since they were accounted based on the strength design approach. So this gamma I, qi, which dictates your factors of safety, here are actually a mixture of probability or statistical values and experts' opinion. Okay, so there's a confusion between the use of such methodology. That's why in LRFD format and in the strength design format, they are specifically defined in the separate guidelines for the methodology being used, either ASD or LRFD. So for the LRFD approach, take note that for the load resistance factor design, the method is different in terms of the provision of the factor of safety involved. So our basic equation for safety, which is a simple R greater or equal to Q, is actually uh, transformed into a little bit of a, uh, a nominal strength multiplied by a reduction factor phi. Okay, so this refers now to your resistance or strength, and this summation gamma I qi refers now to your load or load effects. Okay, so the summation gamma I qi was involved since we all know that loads are coming from different sources like dead, live, earthquake, wind, flood, rain, water, earth pressure, temperature, etc. Okay, so we need to make use of different uh, load factors for us to be able to determine the whole effect of such load combinations. And this is where the LRFD uh, approach becomes a little bit involved in comparing resistance over the load or the load effects. So Rn here is the nominal strength, Phi is design strength, Phi is the strength reduction factor which account for some errors, okay, and gamma I are the overload factor which accounts for some shall I say inconsistencies or inevitable circumstances as far as the load application is concerned. And the subscript I there only refers to an index that will give you the load type, uh, which is, for example, the dead, the live, the wind, etc. So for the values of phi, the reduction factor, which are based on probabilities, the American code uses for tension members 90% for yielding and 75% for fracture. Compression is 85%, beams is 90%, for flexure and shear, fasteners are 75% for all failures, but of course this is referring to more or less brittle or fractural failures. The factors in selection of these values of phi is due to the understrength or the material variability and dimensions. Okay, so we cannot uh, be assured of the exact strength of the material, so we have to account for some reductions. This is also due to inaccuracies in design equations because of our simplification of the formulas. The degree of ductility required on the reliability of the member. Different members have different reliability when it comes to toughness and ductility, and of course the importance of the member. No? So the member is not as critical as the other, so the reduction factor may be uh, higher than the those which are more critical. For the values of summation gamma I qi, these are also based on probabilities. We have this as part of your American code and adopted by the NSCP. Okay, so we will be using some of this, but not all, when we go to some computations. These are all available in the code, so we have no worries about the use of them, because you don't need to memorize them, because I will let you look into to your notes and references when you need them. Okay, just take note that in 3, 4, and 5, the load L, which is the live load, may be reduced to 50% if the live load is greater than 100 psf or 4.8 kilopascal, which is actually very applicable on storages and garages, and also for public assembly loads. For the overload factors, these are actually due to uncertainties and variability in the magnitude and distributions of loads, change in occupancy or use. That's actually the inconsistency on the use of your structure, underestimation of the load effects due to oversimplification of the structural analysis, and the variation in the construction procedure. So in comparison, LRFD and ASD may be compared in terms of this, no? So capacity determination is actually the objective of the LRFD, while allowable stress computation versus actual stress is the premise of your ASD. So the LRFD is limited on elastic, not limited rather on the elastic behavior, while the ASD is limited on the elastic behavior. The response of the member on LRFD is based on linear and nonlinear analysis, while the response on ASD is only based on linear analysis. So for the factor of safety, we take note that the LRFD is based on probability and statistical assessment, while ASD is based on experience and judgment. And in number 5, for the factor of safety, we actually observed a while ago that in LRFD we use multiple factors in order to have a good margin of safety and more reliable values for your computations, while for ASD, since there are only a single factor of safety involved, adjustment in the use of different factors for multiple load combination is not achievable. Okay, so don't that makes one more advantageous to the other, or vice versa. So we cannot predict yet which is the more advantageous unless we come up with a detailed computational comparison of LRFD and ASD. Okay, so that's it for the two methodologies. I'll see you on the next video for some probability-based load and resistance concepts. Thank you very much.